Last month on Enterprise, we brought you the story of unmanned vehicle systems, as they are used generally throughout American business and government. This month, we'd like to bring you the story specifically of this unmanned vehicle system that is being used here in our own community. It's affectionately known as URV, the Unmanned Research Vehicle. To bring us this story, we have two guests in our Enterprise set today. Colonel Dick Borowski, Chief of the Flight Control Division of the Flight Dynamics Laboratory. The Flight Dynamics Lab is one of 4 Air Force Wright Aeronautical Laboratories managed by the Aeronautical Systems Division at Wright-Patterson Air Force Base. And on your right, Mr. Jim Morse, Chief of the Control Systems Branch of the Division. Gentlemen, welcome to Enterprise.
Happy to be here.
We're going to come back and ask you guys a couple of questions in a few minutes, but first let's show our viewers the rather interesting videotape that you have of the URV development team and of the URV actually in flight.
In this laboratory, we do applied research in computers for aircraft control. The goal is to provide a system which can suffer failures without any overwhelming consequences. In an effort to keep the cost of such systems down, we investigate the use of low-cost, commercially available products. A recent spin-off application of such commercially available technologies investigated by this laboratory was in the URV program. A computer chip originally designed as the heart of a production automobile engine control system was adapted to work as an advanced autopilot in the URV. The entire process of transitioning the technology into an operational prototype was done in-house.
Currently under investigation is the capacity of this chip to rapidly alter flight functions to compensate for the sudden loss of part of a lifting surface. The potential usefulness of such a system in combat aircraft is obvious.
The ailerons are the control surfaces which are used to roll the airplane on its longitudinal axis. When coupled with the rudder, the ailerons contribute to performing a coordinated turn. With one aileron ejected, the ability of the aircraft to roll and turn is reduced. The computer-programmed autopilot restores more normal flying characteristics to the vehicle.
This computer and monitor are used to program the URV math model into the autopilot. The graphics are identical to the flight instruments in the URV control van, with the control sticks performing the same functions as those in the control van. It is possible to duplicate nearly every URV flight condition and situation. This reduces the hazard to the URV on initial flights when an untried and perhaps unorthodox control concept is being evaluated.
Prior to launch, the wings are put in place. Meanwhile, all is made ready in the van to record incoming data. Next, the pilot tests the remote controls. The pneumatic launcher is driven into place and the generators are started. Next, the vehicle is placed on the launcher. The vehicle is transported downrange for a final checkout of all telemetry systems.
The telemetry system transmits 34 channels of information from sensors on board the URV down to this recorder. The control console on the right can be used to fly the vehicle from inside the van, and this full complement of instruments gives the pilot visual information such as speed, altitude, direction, and attitude of the flight vehicle. The TV monitor above the control console displays the picture transmitted down from the video camera, which is mounted in the nose of the URV and aids in flying the vehicle by visual flight reference, much like being on board the URV itself.
All systems look good, and the vehicle is ready for launch. At the count of 5, the pilot gives it full throttle, and the launcher fires the vehicle forward at a force of 10 Gs. The bird is up. After several flybys, the pilot signals he is ready for the aileron drop. Inside the van, data from the vehicle is being monitored and recorded for later study. At the right moment, the button is pushed and the aileron is jettisoned. Success. As the aileron floats back to Earth, the bird keeps flying, totally responsive to the pilot's controls. A few more passes, and then it's down for a perfect landing.
That's an interesting video, Jim. Tell us, how does this kind of flight test compare with the cost of conventional methods?
Well, we can operate the unmanned research vehicle for a year for about a fraction of the cost of a manned airplane for one flight.
Wow. Colonel, how long has this program been underway at the base?
Well, this has been about a 2 or 3 year effort for us.
We've often heard, living in the community near the airbase here, the expression fly-by-wire. What does that mean?
Well, about 20 years ago, we were having trouble with the combat survivability of our fighter jets. The controls were operated by mechanical cables that ran out to each of the control surfaces, and if those mechanical cables should suffer some battle damage, the effectiveness of that surface was lost. So in an attempt to improve the combat survivability, we came up with a way to operate those control surfaces through an electrical computer kind of signal, and then we could have a multiplicity of cables going out to any particular surface, and combat survivability improved. Well, it turned out that that not only improved combat survivability, but that gave us the opportunity to use the computer to shape the way the airplane flies. That let us improve the flying qualities of the airplane, make it easier for the pilots to handle. Current airplanes are much easier for pilots to fly than the older airplanes. And it also allowed us to fly airplanes in unusual configurations, like, for example, the X-29, which would be unflyable if flight control is dependent on mechanical systems. We see today that any fighter being designed is going to have fly-by-wire flight controls, and in fact, the 2 airliners currently being designed in the free world that we know of are being designed with fly-by-wire flight controls.
Interesting. A number of the civilian applications then also for this kind of research.
Certainly are.
Jim, what do you see for the future of this program and this kind of research?
Well, the unmanned research vehicle, of course, provides us the opportunity to be able to do some very high-risk testing, things that we would not be able to do with a manned aircraft. And we're able to do them with the unmanned research vehicle because it is not as costly as a manned airplane, and plus the fact that we don't have a pilot, so we do not concerned about the loss of life in the event that we lose the vehicle. We are just embarking upon looking at some reconfigurable flight control systems, that is, systems that allow the control system of the airplane to reconfigure itself in the event that a control surface is lost or damaged, as Colonel Borowski was indicating with fly-by-wire in combat. And the system is able to reconfigure itself so that it can continue to fly. And we can do some of those flight tests where we can actually lose control surfaces or parts of a wing or a lifting surface and explore how well these new reconfiguring systems operate.
Gentlemen, thank you very much for being our guests on Enterprise and bringing us this interesting story. URV, the Unmanned Research Vehicle, being used here in our own community, both to make flying safer and more reliable, and to save all of us as taxpayers millions of dollars in research funds.